Hi, my name is Chu Kingan. I'm a PhD student at McGill University, and today I will present my work on Novice type error diagnosis with natural language models. So this work is done in collaboration with Haolin Ye, Yixuan Li, Tianyun Han, and under the supervision of Professor Brigitte Pienka and Professor Xu Jieshi. Okay, so I would like to bring your attention to why we want to study this Novice type error diagnosis problem. So is this problem a really challenging one, or can we just use a standard compiler to solve this issue? So, so, uh, so to illustrate this, I would like to use this multi-weighting example. So suppose I ask you to write a program that sum all numbers from the list. And this is a possible code written by Novice in OCaml. So here's a recursive functions which use match statements with two conditions to do the sum. Okay, clearly I think we can all spot there's some issue here. If we just pass this program to the compiler, here is a error message we can get. So basically, the compiler would complain that, okay, actually I expect type integers, but here I see a list, right? So it's not good. I will stop here. So to fix this, because both of us know the intention of this program is to do the summation, so we know the true cost of the program should happen here instead of the next line. So to fix this, we just here we just replace this empty bracket with a 0. Okay, now we can fix this program. But the real problem is why we can't use a compiler to solve this problem. The issue is that the compiler is work in a way that it collects all the type constraints when it traverses the program, right? And once they find an inconsistency, it will just report the error. Okay, so our goal here is we want to have an expert sit in the middle. We see a program here, EO type program, and we can, like the expert, point out where the error is. And my topic name of my talk suggests, we would like to use a natural language model to approximate this expert. Okay, and here, I want to briefly mention some recent work on this problem. So as there is a line of work follow the idea of how the compiler works, which is augment typing constraints. Basically, it basically is assign some weights on the typing constraints. Those weights are determined by some expert knowledges, and by adding weights to these constraints, is make the system easily to pinpoint the true error locations. And I think that like I mentioned before, the programmer's intention actually plays a very important role here, and those intentions are hard to model, right? So we use machine learning here to solve these issues. So our work kind of belongs to this category, machine learning track. Okay, right. So right now I want to show you guys a general idea of our methodology. So here, first we have some imaginary true underlying distribution of all possible EO type programs. This is usually an assumption we made in machine learning field. And with this assumption, with this distribution, we can do sampling. We can sample a large collection of EO type programs, and we can have an expert to pinpoint where the true cause of the type error it is. So with this label data, we are feeding this label data to a language model, and train the model. Once it trained, we can deploy the model to a real world scenario. And I think the most confusing part in this diagram probably is the language model. So I will talk more about it. So the language model is just nothing but a probability distribution over a sequence of words. Okay, and it can also be written in this recursive conditional fashion. And I think in 10 years ago, the most successful model to model this uh, language modeling is RNN-based model. It's a variant of neural network which utilize some memory states. As you can see here, once they see an inputs, right, an inputs word, and it will try to predict the next one, which is exactly what the equation described here. Okay, so nowadays we basically we forgot this RNN model. We don't use it anymore because now we have a much powerful, much larger model, which is called transformer model. So I won't spend too much detail talk about all the internal mechanisms. They are very complicated, but they have proven to be very useful in practice. So there is actually not very much science in here to design this mechanism. It just we just find out they are working well, so we use here. So briefly, we can consider the post transform model into two parts. One is called encoder, one is called decoder. So those two parts later involve two very famous language model, BERT and GPT. So BERT actually use encoder, which allows it to see bidirectional representation of the underlying sequence, while the GPT model can only see like one direction. That's their most, I would say, the most difference between them. And the GPT model is usually much larger than BERT, which makes the training very costly and inefficient. So in our study, we use BERT model to do all the prediction. Right. Yeah. Okay. And I think I need to mention about transfer learning, which is very a key reason why language model are so successful. So the transfer learning is also called the pre-training and the fine-tuning scheme. So in the pre-training phase, we pre-train the model on very large, massive data set. This data set unlabeled. So you can imagine this phase as people learn some like common sense tasks, right? And later on, we pre-train the model on some more specific task. These tasks has labeled. So you can imagine this phase as like people do some exams, like English test exams. So they are more specific. But the key idea here is that we want the knowledges learned from pre-training phase can be used later to solve specific tasks. That's why these models are powerful. And with this transfer learning uh, scheme, the language model becomes so successful, it can outperform human in many tasks, ranging from text generation to translation. And it also brings a huge impact to the industry. Like nowadays, Google and Meta, all the big companies are developing their own models, and they achieve like a very amazing performance. Okay, next, yeah, next interesting part is that we want to show you guys how we transform this language no, type error diagnosis problem into a problem that language model can handle. So first we have our uh, old simple program here, and we can use a tokenizer to tokenize it into a list of tokens, and these tokens list of tokens will serve as our input to the model. In addition to that, we will have a list of binary digits, and those labeled by human experts. So these digits with zero represent this corresponding token has nothing to do with type error location, and one means this token is related to type error. Okay. So after we have this transformation, we just pass all this input into the model. So here we just regard this model as a black box and let the model do all the calculations. So the result is like for each token we have calculate this probability, corresponding probability, whether this token, how much confident you believe this token is related to the type error. Okay. So next, so data sets actually play a very important role in the machine learning field, because machine learning is basically data driven. So here, in order to compare with previous work fairly, we use latest data set as our evaluation data set and also our fine tuning data set. So because we want to transfer learning, so we need to have some pre-training data set. So here we basically we collect two data sets. One is we crawl from GitHub, and another one is a homework data set. Is basically we collect those data from homework submission at McGill University, and based on our some analysis, we found out homework data set and native data set has many things in common because they are both written by beginners, whereas GitHub data set don't share lots of similarity. So okay, after that, yes. So the choice of models. So first, we would like to show you guys the techniques 10 years ago. Is the first one is just a RNN-based model. And next, for the language model, we have BERT trained from scratch. This is model we trained from scratch, no transfer learning. And also we have model of 4 different sizes. And we have CodeBERT, which is pre-trained on some popular languages, Ruby, JavaScript, but exclude OCaml. And then we also have a model pre-trained OCaml. So this model is like it learns OCaml at the first place, at the very beginning. Okay, so here is our evaluation section. I think the very first important question is what is a good metric to measure how this model perform, right? So I will let my collaborator Haolin take over this part to answer this question.
Thank you very much. Hello everyone, I'm Haolin. I'm a bachelor student studying at McGill University. I'm going to answer the question asked by Alan. So what's a rigorous metric for this project? I think it's crucial to understand what do we mean by rigorous. So for a given prediction, I think the metric for it to be rigorous, it should tell whether this is a good or bad prediction, just like how we do. So first, I think it's useful to just picture a general function. Doesn't have to be in OCaml. So here I have like blue bars to represent this is a general program. And for the red bars, it's just error locations. So what we expect the model to predict for us. So the first kind of predictions made by the model could be these thin green bars. And we think this set of predictions is not precise because it just covers a very small portion of the error locations. So we don't want to evaluate these predictions to a very high score. So let's just keep this in mind and put this aside and picture the same old example. And for the second type of predictions we have are these like longer green bars, but many of them are actually outside of the error locations. Some of them are actually touching the error locations, but even if they do, there's just this very little overlap between the predictions and the error locations. So we think this is neither a good set of predictions. This is neither a good one. Also keep this aside. And finally, we have something good. So here on the screen, you can barely see some red. So the predictions made by the model covers almost all the error locations. And we think this is good. This is what we expect the model to predict for us. And with all these three kind of predictions, we come up with this accuracy formula, which takes in P stands for predictions. So like the green bars you have seen, and L is the error locations. Yeah, that's basically how we came up with this evaluation metric. And I will give the mic to you.
Okay, next questions. I think we would like to know how different models perform in general. So here we show all models we have right now to on the evaluation data set of net. As you can see, our large language models generally outperform other models in general, right? We outperform a native model at least 10%, and constraint-based methods like OCaml and Sherlock, they are generally about 40%. Okay, OCaml compiler is even lower, and it's only slightly better than some random guess. Okay. Yeah. Another interesting thing is that because the language model's prediction is actually a probability, and probability we can think of them as a measure of the level of confidence. So if we think about this scenario, so we only let the model make prediction when it is very confident. So in that case, we look at this part when we increase the threshold of the prediction, we see that the native model, they're also machine learning model data driven. They are not robust on this side. So you can see there is a huge accuracy drop here, but our language model seems to be very confident in here. So this prediction are very robust, means the model is very confident about its own prediction. Okay. Yes, and another interesting thing is it's also in our design of the models. So it's like we want to know what factors actually affect the model's performance. So here we choose the size factor into our first study. So as you can see, if we increase the size of model, you will gradually see there is a drop in the loss curve, which means you will get better estimates once you increase the size of the model, which usually in turn give you a better accuracy overall performance. This law it becomes like a rule of thumb in machine learning field. So when you want to solve some problem, you always use bigger models instead of the small models. Okay, another factor we would like to think about is about transfer learning. So here we use the BERT model as our baseline. So with code BERT and the BERT pre-train as our example of negative transfer learning, because code BERT doesn't involve any knowledges on OCaml, right? So another BERT pre-train in the pre-training phase, it doesn't see any special on OCaml code. So with for these two examples, you can see they perform less well as a normal BERT model. But if we pre-train on OCaml code, which is the OCaml BERT, you will see there is a slightly better performance, which is the line most lowest line there. So we can conclude is that from negative to positive transfer learning, you will see some good boost in the performance. So this is also generally true in the machine learning field. Okay, so last one is I think is also most important one in the real world use of these models is how well these models generalize to unseen data. Meaning that here, okay, if you look at the first two columns, is training on the test on the same data set, which is you investigate their performance on the same data set. But this is not always the case we do in a real world scenario. In a real world scenario, we always see something we never seen before, right? So the last two column is what we really care. So because you can see for the bidirectional long short-term memory model, which is the RNN model, the accuracy drops from 40-ish to 7 and 8, huge decline, right? And also 7 and 8 makes the model almost useless here. But for the language model or camera bird large, for example, even we drop 50% from its highest accuracy, we still have 60% accuracy. This is good enough outperform any other methods we have right now. Okay. Lastly, I would like to briefly discuss our the advantage and disadvantage of our method here. So the first one is our model could easily outperform current state-of-the-art methods by a large margin, even under a very rigorous metric. And second one, in this old design of this pipeline, we don't need any feature engineering, no human expert knowledge, and also no type constraint analysis needed. And also, the model itself is language agnostic, meaning that you can transfer to any other language easily, as long as you get collect enough data and do all the data pre-processing properly. And also, it is also task agnostic. So as long as you can transform your task to a task that language model can handle, you can always do that, right? And okay, so here also comes some drawbacks. I think this is also a very awkward moment for large language models, because they are. If you want the so thing is, if you want a model to perform better, you have to make it large, become larger. And the downside is that the cost of the training computation requires for training this model is growing exponentially. And now you can see for those, I think that I regularly remember for just training GPT, the cost of just training a model is about like $1 million. You can imagine the next two models is like only large companies can do that right now. And also with the growth in size, the need of the data set is also growing. So if you want to achieve a GPT level performance, you need roughly 500 gigabytes of data. So it is impossible for a small task like we present here. Okay. So for the future work, because in this work we don't explicitly consider the structure information, we just transform the program into a flattened list, right? And so there is no structure information involved here. So next, we plan to think about how to utilize the structure information here. So our rough idea is to use a graph neural network, which is a network that usually work well on graph. Okay, and we see maybe we can put this together and give some interesting results. Okay, that concludes all my talk. Thank you.
Questions?
Hi.
You showed us a picture of programming example. For the recursive handling of head and tail. Could you also handle more traditional iterative programming style with ordinary loops instead of
Ordinary loops. I think so. Because for the model, it doesn't need to understand what's the meaning of the program. It basically just say it as a natural language. So even a while or other loop things, it just I think the internal mechanism it may pay attention to. Okay, it's a loop, so I made to make some special calculation. But I think in a big picture, you don't need to do anything about that. You just treat it as a natural language and feed it into the model and let the model to do the prediction. Yeah. Hi.
No, sorry. The last slide you showed that you may want to use this graph system.
Yes.
I wonder, could you simply, like as a point in the middle, like a low-hanging fruit, if you parse OCaml or whichever other language, and you just add a lot of parentheses to forcibly disambiguate all possible precedence operator or other thing, you sort of get an encoding of the structure of the upstream syntax tree in the syntax. Do you think that will help the model?
Yes, I think that definitely help. But I think our idea here is one we keep this pipeline as simple as possible, because here we just want to show you guys. So by just do this simple check, you still get a good result. But I can imagine with more like yes details, careful engineering, you can even get a better results. Yeah, of course. Yeah.
It seems you just mentioned the error locations instead of error messages. I'm wondering that it seems weird to me that you just point out that where it's wrong, but not why it is wrong.
Okay. Yeah. So yeah, you asked a very interesting question because here in most cases, I think machine learning can be think of as a function estimator, approximator. So it's like a work in an end-to-end fashion. So you show you something, it give you something, right? It give you some feedback, but how it makes this decision, how it makes getting the results in internal exam is largely I think it's still open problem. It's unknown. Yeah, the interpretability of the machine learning is still remains to be very important but unsolved questions.
Okay, thank you.
Problem. Yeah. Hi. Yeah.
Have you tried to, I guess, evaluate the robustness of this tool, maybe by example, renaming variables or taking an expression that isn't involved in the type error and rewriting it to an equivalent expression that might look different to see if that changes the results of your predictions?
I think it definitely would, because the model it works in like it's all about the distribution. So if we train something is in, and if you give something that's very similar to it, it can definitely work on that. But if it's largely different, but semantically it is equivalent, I don't think the model could do that. But here is a quick remedy is that you do the transformation, and along with that data, you can give to the model as augmented data. So hopefully that model will know how to do that. Okay.
And do you think maybe having like the t-structure may help it?
Yeah, definitely. Yeah.
I have a question
Sure.
regarding your data set.
Yeah.
You mentioned it's the label is down by accident.
Yeah.
But we know that human can make mistakes.
Yeah.
Also, the compiler also gives you
Yeah.
like error message. So how do you measure the validity of your data?
Okay. Yeah. I think it's also you asked a good question. So I think the reason we want to have label data because we trust the label is always true. But if there is some violation in that, it is also called data poisoning. So if that happens, it will significantly reduce the performance data. But here we just use the same data set of previous work because we believe it's true because we want to do a very fair comparison. So we just assume the data set is okay to use right now. Yeah. Hi.
Could you give some intuition on how your accuracy scores relate to the utility of the tool? So intuitively, I guess, like I would think that 0.5 accuracy or 0.6 might be more confusing for a beginner. Right?
Yeah, sure. I think here, if you go back to this, this kind of example, right? So we cannot exactly pinpoint the sub expression that goes your type, but we can cover like a very big percentage of that part. So it's like give the users a better guidance. So you can look at this part. It probably goes around here. So the rest we just let the user to decide. Okay, where exactly you look at.
And in using your tool, you found that this 0.5 is sufficient to be.
Yes, exactly. I think later we will provide a user study on how this thing works. Yeah.
Well, that's great.
Hi.
Yeah,
So,
thank you. How do you define, like, this tool is being used to locate the source of an error.
Mhm.
How do you define what is the correct location? Is it the part of the code that you have to change in order to fix the error? Or what is the reasoning behind, like when the expert is labeling this data, they say, oh, the real error is actually located here. Why do they say it's there and not some other location? Location the compiler reports.
Yeah, I think it's really depends on how people think where the issue is.
Right, so it's just up to the expert.
Yeah, it's up to the
Okay, that's
to the expert knowledge.
So thank you very much.
Thank you.